Hello everybody, myself Jacob Prasanna Kumar. I'm an alumni of ITBSU Varanasi. Right now I'm working in the GATE Academy. So with the GATE Academy, people are here with a new video on the subject of strength of materials. So this will be on the topic of shear force and bending moment diagram. So the title is written here. So first of all, I will start with the concept of beams, and at the end of the lecture we'll be having an idea how to draw shear force diagram and bending moment diagram for any type of loading acting on a particular beam. So let me start with the definition of a beam. So let's see the slide here. We see a member here. We'll be calling this as a beam only when it is experiencing bending. So to create bending, we should have a force which is acting in this way. So the load must act in transverse direction to the length so that it will be causing bending. So one thing we come to know that here, to cause bending, the load must act in transverse direction. Now, not only because of loads, because of moments also we can cause bending. So to make you understand regarding the bending because of moments, I had to explain you regarding the moments here. So how the moments are actually arising, what exactly do you mean by moment or torque or turning effect of a force. So this thing I have already taken in the video of torsion. So for example, if you have a pulley, and here it is pivoted about the center here. On this pulley, if you put any force which is passing through center, that will not be causing any type of rotation. But if you are putting a force which is acting some eccentric to the center, this will be creating a turning effect. So the turning effect is measured in terms of torque, and it is given by product of R and F here. So from our common sense, we can say that like this force is going to make this pulley to rotate in clockwise direction, but if you want to quantify it in a technical way, we have to use right hand thumb rule. So to use right hand thumb rule, we have to put your fingers in this way. Your 4 fingers will be around the radius R. So you can put your fingers in this direction or in this direction here. But after keeping like this, you have to curl your fingers in the direction of the force F. So if you are putting your fingers like this and you are curling in the direction of the force F, you see your fingers are getting curled in clockwise direction. So the torque, whatever it is produced here, the turning moment whichever produced here, or the moment whichever is produced here, is a clockwise moment or clockwise torque or clockwise turning effect. So generally the sign convention is clockwise torques are taken as negative, counterclockwise torques are taken as positive. So this is a sign convention which we follow for the direction of moments or torques. Now you see that here, this force is acting on XY plane. So it's having a component in X direction like this. If you resolve the force along X direction, it will be having X component in this way here, vertical component in this way, F suffix Y here. So it's acting on XY plane, but this is giving rise to rotation about Z axis. So here you have to understand that if you are applying force in X and Y direction, the rotation will be on Z direction. If it is on Y and Z plane, it will be about X axis. The moment or turning effect will be about X axis. That means the member will be going on rotating about X axis, just like this is rotating about Z axis here. In the same way, if your forces are acting on X and Z plane, then your rotation will be about Y axis. This thing we must take into consideration here. Now let's come back to the concept of beams. If you take a member and see the moments acting on that, let the moments be in this way. Before putting the moments, we should have a particular coordinate system. X direction, this is Y direction, and this is Z direction here. So one moment is about X axis, M suffix X. One moment is about Y axis, M suffix Y. And one moment is about Z axis, M suffix Z here. Now if you take these 3 moments here, M suffix X or moment about X axis will be creating torsion. It will not be creating any type of bending. But if you take the moment which is about Y axis and Z axis, for instance, you take the moment about Z axis, if your member is like this, MZ, so this will experience bending in this way. So this is experiencing bending here. So we see that here, if the moment is about transverse axis, maybe Y or maybe Z, according to this coordinate system here, this can cause bending. So we can summarize the definition of beam that if a member is experiencing loads or moments in transverse direction or moments about transverse direction, so that will of course will be experiencing bending, so we call those members as beams. So the definition of beam is in this way here. So never have a confusion that the horizontal member should be called as beams, vertical member should be called as columns, like that one. Beams can be horizontal, vertical. Columns can be horizontal, vertical. So there is no restriction in terms of the position here. So how the loads are acting, how the member is experiencing the deformations, etc. So we'll be taking according to that one here. So we see that beam must experience load or moment about transverse directions or along transverse directions. So you can write down the definition from the slide here. So it's given like this. Members which are subjected to loads or moments in transverse direction to the longitudinal axis are called as beams. Now we'll see the types of supports. To support the beams, we require different types of supports. Let me show you the simplest supports which we generally use to support the beams and which generally we take into consideration and do the analysis in the subject of strength of materials. There are mainly three here. You can see the slide here. Roller support, hinged or pin support or fixed support. So if you see the pictures, they'll be looking like this one here. First one is roller support here. Now, let me explain you when we're going to use this roller support. If you are expecting your beam to be supported in vertical direction or only in one direction, basically. So in this diagram here, you have to support the beam or you have to support the beam in vertical direction here. So we're going to use roller support here. So we can't move the beam in vertical direction. It is fixed. It is firmly fixed in that particular direction here. But if you would like to move the beam in the horizontal direction for this particular diagram here, so we see that here it can be easily moved. If a force is acting on that, it will be moving with a particular acceleration corresponding to that one. So if you would like to restrict the beam in only one direction, you will be going to use roller support here. If you want to restrict the beam in both the directions, that means two perpendicular directions, horizontal, vertical, x direction, y direction, etc. So we can go with either hinged or pin support or a fixed support here. Basically, they are giving some reaction forces and those reaction forces are making this beam to become fixed in that particular direction or not movable in that particular direction here. So let me show you the reaction forces here. Roller support here. If you take the roller support will be like this. So if you take the free body diagram of the beam like this and you follow a coordinate system, standard coordinate system, x and y. So here we can't make this beam to move in bottom direction. So there is a restriction in y direction, r suffix y, or reaction force is there here. But there is no restriction along x direction. So if you are applying some force, it will move. So we are not going to show any restriction or restricting force along x direction here. But if you go with the hinged support, it will be like this. So this will not allow the beam either to move in x direction or y direction. So if you draw the free body diagram of this particular beam, you will be having two reaction forces. One is along y direction, one is along x direction. In the same way, if you go with this fixed support, the fixed support will be looking like this. And if you draw the free body diagram of this particular beam here, you will be having reaction forces just like the previous one. Ry will be there, Rx will be there, but there is a reaction moment also. Because here, if the beam is experiencing any load like this one here, it is free to rotate about this point here. But here, if it is trying to rotate, it will not be able to rotate here. Basically, the beam having a fixed support will bend in this way, but the beam having a hinged support will be bending in this way. So here there is a restriction moment is there, which is not making this element or the element which is in the vicinity of this particular fixed joint to rotate. So there is a reaction moment here. So reaction moment I am taking in this direction here. So basically the forces, reaction forces which are actually unknowns, Rx, Ry, M0, all these values are shown in positive directions. Rx is shown in positive x direction, Ry is along positive y direction, M0 is taken in anti-clockwise sense because moments in anti-clockwise sense are taken as positive. So after doing the calculations, Later I will be explaining you how to or which methods you have to use to get these unknown reaction forces and reaction moments here. So if you get a negative sign, that means that they must be kept in the opposite sense. That will be the conclusion for the particular thing here. Okay, now if you go further, we see the types of beams. So there is a slide here. So the different names are given for the beams based upon the combination of supports we have. So if a beam is experiencing only or having only a fixed support on the one side, it is called as a cantilever beam. So if a beam is having a hinged support and a roller support on both the ends, we call that beam as a simply supported beam. So just like that, we see overhanging beam, continuous beam, fixed ended beam, cantilever simply supported beam. So basically, most of the questions will be asked from cantilever beam and a simply supported beam. So whenever they use the name, and if they're asking you any question without a diagram, you must be able to draw the diagram on your own. Now let's see the types of loads. So if you see the types of loads on this diagram, there are three types of loads here, or which are majorly used loads here. So first one is uniformly distributed load. So this uniformly distributed load is having same amount of intensity along that particular length. But if the load is acting at a point, we call it as a point load or concentrated load. And if intensity of the particular load is varying along the length, we call it as a varying distributed load. Okay. Now, let's enter into the main part of this thing here. So, we have to draw the shear force diagram and bending moment diagram. But to draw the shear force diagram and bending moment diagram, we must have to know the values of unknown reaction forces. That means the Rx value, Ry value, and M naught value here. So we use some equations. Those equations are basically the condition of static equilibrium, or the equations of static equilibrium there. Because the beam must be in equilibrium to experience stress, so we're going to keep it in equilibrium. So we're going to apply equilibrium equations and get the values of unknown reaction forces. So I will give you the method here, I'll write down the equations here, and later we'll solve one gate question showing you how to use these equations and get the answer. So let me show you the equations here. If your member is experiencing loads in three directions, or x direction, y direction, z direction, then your equations will become sigma fx is equal to 0, that means net force in x direction must be equal to 0, sigma fy is equal to 0, sigma fz is equal to 0. In the same way, net moment about x axis must be 0, net moment about y axis must be 0, net moment about z axis is equal to 0. As the loads are there along x direction, y direction, and also z direction, so the loads along y and z will give rise to moment about x axis. Just like that, the loads along x and z direction will give rise to moment about y axis. In the same way, moment about z axis. So all these things should become 0. Then only the material will be in equilibrium. Okay, but if you go with 2D case generally, so let's consider the loads are there in x and y directions here. So net force in x direction must be equal to 0. Net force in y direction is equal to 0. In the same way, you should be getting net moment about z direction is equal to 0. As the loads are there in only x direction, y direction, so they will give rise to rotation or turning effect or torque or moment about z axis. So this equation must be there. So mostly the questions given in the subject of strength of materials from this chapter are 2D loading cases only. So we have to solve these three equations. So we rarely go with this type of loading case there. Let me show you one question or example and get the answer for that one. So you can copy the question from here. So it's given that a mass of 35 kg is suspended from a weightless bar AB, which is supported by a cable CB and a pin at A. So pin means a pin joint there, as shown in the figure given below. The pin reactions at A on the bar AB are. So if you see the next slide, we see the options here, A, B, C, D. So there are distinct values for Rx, distinct values for Ry. So let me draw the free body diagram for the beam based upon the diagram given in the question, and let me write down the equilibrium equations and give you or find out the values of the horizontal reaction force and vertical reaction force at the point A. So if you take the free body diagram of the beam, it is like this. This is point A. So at the point A we have a hinged support, so AX will be there and AY will be there, and at point B we are having a weight here, so 35G, and you're having tension, this is T. So it's acting at some angle here, so anyways we know the angle here in terms of the ratio of the distances, so it is 125 millimeters and this is 275 millimeters. This is like this. So here what we're going to do is, we're going to resolve this force or resolve this torque in horizontal and vertical direction. T cos theta, T sin theta. Now let's write down these equations here. So if you write down these equations, first one, net force in x direction is equal to 0. So this gives you the answer that Ax minus T cos theta is equal to 0. If you take net force in y direction is equal to 0, this gives you the equation that Ay minus 35G plus T sin theta is equal to 0. Now we are left with the third equation, that is moment about z-axis. So you can take that moment about the point A or point B also, but to cancel out the moments because of Ax and Ay, so we'll go with the point A itself. Now if you take the moment about this point, moment about z-axis is equal to 0. So we see that here, if you write down the equation, about point A, 35G is acting at a distance of given by 275 millimeters. So for instance, I'll be taking this one as L here. So I'll be getting moment because of 35G is equal to given by 35G into L. But here, this one is acting in clockwise direction, so you'll be taking it as negative sign here. Now in the same, if you take the moment because of T sin theta, that will be plus T sin theta into L is equal to 0. So from this third equation, equation number 3, so we are getting that 35G is equal to T sin theta. We got one answer here. So we got three equations here. So 35G is equal to T sin theta and equation number 1, equation number 2 here. So if you solve those three equations, you're going to get the answer as D, as it is shown in the slide here. So Rx, or basically Ax will come as 755.4 newtons here, and Ry or Ay will come as 0 here. Okay. So this is how you have to evaluate the unknown reaction forces, and from that we'll go on to find out the shear force diagram and bending moment diagram. So now let's go with the shear force diagram and bending moment diagram part. So what is shear force diagram? What is bending moment diagram? Understand carefully. Let's take a beam. So this transverse load is there, P is acting here. So it is supported by some reaction forces. Let's take this one as R1, this one as R2. So because of the load P, it will experience bending. Now you see that because of the load P, it is going to experience bending, that giving rise to some deflection at every point here. So although the load is acting at some points, that means along the length direction, the load is acting at some distance. So load is acting at this point here, but the effect of the load, that means the deflection is there throughout the length here. That means the load is getting induced, or the effect of the load is getting induced along the length, whole length here. But the amount of induction will be something different. So in the shear force diagram, we're going to draw or we're going to plot the induced value of shear force because of the application of this load P along the length. So we're going to plot the curve here, somewhere else it will become positive, somewhere else it will become negative, and it will come like this one. In the same way, if you see this diagram here, the element which is here, this shaded part here, which was like this, but after the application of the load P, it got turned in this direction. It got rotated. That means initially it was like this, horizontal, vertical, but it got rotated by some angle here like this. So that means some turning effect is getting induced here, some rotation is being induced here, some torque is getting induced here, or some moment is getting induced here. But amount of moment, or basically the amount of rotation that is actually occurring, will be different based upon the element I am considering. That may be near to the load, away from the load. So that depends from element to element here. So in the bending moment diagram, I basically find out this induced value of the bending moment along the length of the beam here. So using these two results, we're going to find out shear stress induced inside the beam using the shear force diagram, and we're going to find out the bending stress induced inside the beam using this bending moment diagram there. So that is the importance of this drawing of this shear force diagram and bending moment diagram in the subject of strength of materials. Without the use of, or without the understanding or the knowing of this technique regarding drawing of shear force diagram or bending moment diagram, we will not be able to evaluate the stresses induced inside the beams or the members which are actually experiencing bending. Now let me go with an example and let me show you how to evaluate the bending moment and shear force diagram, shear force value at a particular location. Let's take an example. A beam is there which is experiencing load at the center. So you take this as R1 and you take this load as R2. So as it's acting in the center, this will be L by 2. This will become L by 2 here. So if you apply equilibrium equations, you will eventually come to a conclusion that R1 and R2 is equal to given by P by 2. R1 is equal to P by 2. R2 is also equal to P by 2. So you got all these values here. Now I am interested in finding out the value of shear force or induced value of the shear force at this particular distance. Let me take this distance as L by 4. Later we will find out the bending moment also. So to find out shear force, what I am going to do is, I will slice off or I will cut the beam into two parts at a particular point. So after cutting that, I will be getting the two sections or two parts in this way. So here I will be having P by 2 and here I will be having the remaining parts. So load is P here and this distance is given by L by 4. So this is L by 2 and this is P by 2 and so you can evaluate the distance of this length also here. So here the induced value of the shear force can be taken in this way upward. So here the reaction force must be there. Both must be cancelling out because net force at this section is equal to 0. Okay. In the same way I can go by the reverse condition also. So here we'll be having shear force V here. So the arrangement is different. So either you can go by this way or in this way here. Anyways, you'll be getting net load is equal to 0 at this particular point because no force is being acted here. Now, to evaluate the value of V, we again apply equilibrium equations. When the whole body is in equilibrium, individual parts will also be in equilibrium. So I will evaluate for each and every part here. Let me see what's the value actually I'm getting. If I go with this one, the first section here, I will get the equation that load in vertical direction must be equal to 0. So I'll get V plus P by 2 is equal to 0. So this implies that V is equal to minus P by 2. In the same way, if I go with this one here, I'll get the equation that minus V minus P plus P by 2 is equal to 0. So this implies again V is equal to minus P by 2. So you go either by the left part or the right part, you'll get the same answer. Now let's see whether this happens in the same way regarding this arrangement or not. If you go with the first one, you'll get minus V because V is acting in downward direction, P by 2 is acting in upward direction. So minus V plus P by 2 is equal to 0. This implies that V is equal to P by 2. Okay. In the same way, if you go with this one, you'll be getting that plus V minus P plus P by 2 is equal to 0. So you'll get V is equal to P by 2. So we see that if you are going with this arrangement, we will get V is equal to minus P by 2 minus P by 2. But if you are going with this arrangement, we'll see V is equal to coming as P by 2. So there is no strict conditions or strictness regarding the sign. So whenever a question is given, immediately you can either go by this arrangement of this particular shear force V or you can go with this arrangement also. So if you are going with any one of them, you'll be getting only one sign. So there is no strictness regarding the sign here. In the same way, let me show you for moment also. If I am interested in finding out the bending moment at this particular thing here, I can take like this, M here, about this point. If it is anti-clockwise means here it should be clockwise. So anti-clockwise, clockwise, here clockwise, clockwise here and anti-clockwise here, M. So I have to evaluate the value of M here. I will evaluate for the first section here in the same way as I have done for the shear force. Here I will get the distance is L by 4, M anti-clockwise, V is passing to the point here. So bending moment corresponding to shear force is equal to 0. So M is anti-clockwise, M, P by 2 is there, distance is L by 4. So that is giving rise to rotation in clockwise direction. Because the center point is this much and I am putting my fingers like this. But the force is acting in this direction, so I can't curl like this, so I'll put fingers like this one. So curling is clockwise. So like that you can check the direction of the moment for each and every part. So the moment because of P by 2 is in clockwise direction, so negative, so that it comes as the magnitude is equal to PL by H is equal to 0. That means M is equal to PL by H. In the same way, if you do for this one also, taking moment about this point, okay, so P will be creating, so this P will be creating moment in clockwise direction, this P by 2 will be creating moment in anti-clockwise direction. but this V is passing through this center, so no moment because of shear force V. So here also you will get M is equal to PL by 8. You can check it. But in the same way, if you do for these two cases, you will get M is equal to minus PL by 8, and again M is equal to minus PL by 8. So if you go with the first fashion, first arrangement, you will be getting positive. If you are going with the reverse condition, you will be getting negative. So there is no strictness regarding the sign of the bending moment also. So to have a sign, to distinguish between a positive value and a negative value, we should follow one sign convention. That sign convention comes from the concept of sign for stress components in 3D loading case. Let me show you how. So in a 3D loading case, we have 6 independent stress components: sigma x, tau xy, tau yx. Sorry, this will come as tau xz. This sigma y, sigma z, tau yx, tau yz, tau zx, tau zy. So here we know that like tau yxz will be equal to tau z, zx, tau xy, tau yx both are equal, tau yz, tau zy both are equal. So 6 independent stress components are there. Now, so let's go back to this concept how we actually give the sign value for a stress components like tau xy, tau yz, etc. here. So if your member is experiencing loads in 3D, so loads are there in x direction, y direction, and also z direction, but eventually all the loads are summing up to 0, or all the moments are summing up to 0. So net moment is equal to 0, net force is equal to 0, the body is in equilibrium. Now to find out the stress components, because these stress components will help us to find out the maximum principal stress, minimum principal stress, maximum shear stress. So let's go back to this concept of finding out the sign for these stress components here. So what we're going to do is, we will take a certain coordinate system, x, y, and z. So we'll take the planes. Okay, so planes means positive x plane. Positive x plane we know. Positive x plane means basically our yz plane having normal along x-axis. So basically we never use these words as yz plane, xz plane like this. So positive x plane means the plane which is having its positive, its normal along positive x-axis. Positive y plane means the plane which is having normal along positive y-axis. Positive z plane means normal along positive z-axis. In the same way, negative x plane, negative y plane, negative z plane. Okay. So now what you're going to do is, you're going to slice off this body, 3-dimensional body, using positive x plane. When you slice off using positive x plane, you'll be getting a cut like this, and one plane will be there which will be exposed towards, or will be having a normal along x-axis. So after slicing off, it will be coming like this one. So if you take down the resolution of the forces acting on the particular plane and taking down the corresponding stresses, they would come like this one. So you have normal stress, you have shear stress, you have shear stress. Because a normal of the plane is along x-axis, so the force which is along x-axis will be causing normal stress. So this is normal stress sigma, shear stress tau, shear stress tau. Because these forces correspond, the forces correspond to tau and tau are along the plane, so they'll be causing shear stresses. So here we see that the notation is given, xy, yx and all these things here. So generally sigma ij or tau ij is given in such a way that where I is equal to the plane on which they are acting. Okay, j is equal to given by direction of the particular component. So if you take this one, sigma, this take tau and also this one, all these three are lying on x plane. Positive x plane, positive x plane, positive x plane. And now the direction. This is along x direction, this is along y direction, this is along z direction. All these three are positive directions here. So we'll be getting like this one. Now in the same way, if you slice off using negative x plane, so we'll be having a sliced off plane which will be exposed from the back here. So here we'll be getting the stress components in these directions. So this is a normal stress, shear stress, shear stress. All three are lying on negative x plane, negative x, negative x, negative x. Now the directions, negative x, negative y, negative z here, sorry, this is negative y. So the product, ultimate product will become xx. So sigma xx, this will become tau xz, this will become tau xy. So you'll be getting like this. So to make the product become positive, I have intentionally taken the directions to become negative. So we see that here on the positive planes, directions to be taken in the positive directions. On the negative planes, directions to be taken along negative directions, so that the stress components will become positive. So the positive sense of tau xy will be in such a way that if it is occurring on a positive x plane, it should be along positive y direction, and if it is occurring on negative x plane, it should be along negative y direction. That's the meaning of this one here. So we're going to use the same thing to find out or to derive the sign convention for shear force diagram and bending moment diagram. Okay? If you take a beam like this, which is experiencing loads and experiencing bending moment, you take a coordinate system like this. This is x-axis, this is y-axis, and this is z-axis. Now let's slice off this plane. If you slice off the plane and make it into two parts, so I'm slicing into two pieces here, you will get one view like this, another view you will be having in this way here. So you see, after slicing, this is the plane having its normal along positive x-axis. So this is the plane, whichever is not visible here. This is the plane which is having its normal along y-axis. So on this plane, if you are interested in finding out or drawing sigma x, tau x, and tau yx, or tau xz, you will be having in this way. Sigma x will be along this direction, tau xy will be in this direction. Tau xz will be in this direction here. But anyhow, we are going with vertical loads here, the shear force will be taken in this vertical direction itself. Or the shear force will exist in vertical direction itself. Because as the load is not there along z direction, so you will not be getting any shear stress along z direction. So tau xz will be not shown here. Tau xy is shown here. So tau xy will be positive if it is acting on a positive x plane and acting along positive y direction. In the same way, if you take tau xy on the negative x plane, it must be along negative y direction. So you got tau xy here, you got tau xy here. So you have to use the same thing here. So if you multiply this area, you will be getting the shear force. So we will take that one as V here. So that means that if you are taking a beam and cutting out into two pieces, so the left part, if you are taking, this is the left part. So the upward force should be taken as shear, positive shear force, and downward force should be taken as negative shear force on this remaining part here. So if I draw the side view of this diagram here, you'll be getting like this. If this is the beam, after cutting this, so the left part should be taken like this, V, to be the positive shear force, and if you take the right part, your shear force should be taken in the bottom direction like this. The same thing for the moments also. So if you are taking moments, because anyhow on this beam, the loads are acting on x and y plane, the moment will be about z axis, which will be causing the bending. So when the moment is taken on positive x plane here, it should be taken in positive direction. That means anti-clockwise direction here. Okay, so here it will come as anti-clockwise direction like this. So if you are going with moment on negative x plane, it should be along negative direction. The same concept we are applying for this moment also here. So negative direction means clockwise sense. So it should come in this way here, yum. So here it will come in this way here, yum, like this. So here also yum here. So either you go by the left part or right part, you will get the same magnitude or same value in terms of sign also for the shear force or bending moment. Okay, so to have a positive value of shear force, you have to go in this way here. Okay, so this is how we're gonna use the sign convention here. So I am summarizing the sign convention for shear force diagram and bending moment diagram here. So for a shear force diagram, if you take the beam here, so the section part of the beam here, some part having some length as dx here. So this is the positive x plane. If you take the coordinate system in this way, this is x and this is y here. So shear force, so upward force should be taken as positive, downward should be taken as negative. So this is the positive sign convention here. So if you take the reverse, it will become negative sign convention. In the same way for bending moment also. So this will become positive when you are having anti-clockwise moment on positive x plane, clockwise moment on negative x plane. So this phenomena where the bottommost fiber is experiencing tension, uppermost fiber is experiencing compression is called as sagging. So if you take the reverse one, that means negative sign convention. That means on the positive plane you must have negative direction, clockwise, and here it should be anti-clockwise. So this phenomena where the member is experiencing tension in bottom fiber, compression upper fiber, sorry, the reverse. So tension in the upper fiber and the compression in the lowermost fiber, this phenomenon is called as hogging. Clear? Now I will take some examples and show you how to draw the shear force diagram, bending moment diagram for those examples there. First of all, I will go with simple examples. Now I'm going to take two examples, which are very simple examples. Afterwards, I will take a previous gate question and end up this lecture. So the first example is cantilever beam with point load at free end. So it will be looking like this. It's a cantilever beam having a load W, length as L. So what you have to do is basically, first of all you have to get the free body diagram and find out all the unknown reaction forces. So this will come like this. Load is W here, and if you take the reaction forces, Ry upward, Rx, reaction moment m0. So if you do the equilibrium equations and solve them, you're going to get the values as like this. So Ry will come as W, Rx will become 0 and m0 will become W into L. So this length is L. Okay, so to draw the bending moment diagram, I am making a cut. I will take the left part or right part, I will get the same answer, so I will go with the left part here. So I am taking the left part, which is having a length as X. So here I have load as W, and here the moment is given as W into L. So I would like to draw the shear force diagram. So shear force is taken in this way. So it's a positive X plane, so upward direction, positive direction. Okay, so if you want to draw for the bending moment, so M should be taken anti-clockwise like this. So first of all, I will write down the equation for shear force. So if you write down the shear force equation by applying equilibrium equation y direction to be 0, you will get V plus W is equal to 0. So this implies V is equal to minus W. So if you would like to draw the shear force diagram, it will get in this way. This is 0, length is L. So this will come as minus W. So from x is equal to L to x is equal to 0, it will be minus W itself. In the same way, if I have to write down the bending moment equation, it will become like this. So at this point, M is anti-clockwise. So M anti-clockwise and WL anti-clockwise again. So plus WL. But W is there at a distance of x in clockwise direction. So minus W into x is equal to 0. This implies that M is equal to W of x minus L. So if you draw the bending moment diagram, it would come like this. M, this is x, 0, L. At x is equal to 0, the bending moment value is equal to minus WL. And x is equal to L, it will become 0. So this will come in this way. Minus W into L. So this is how you're going to draw the bending moment diagram. Let's go with the next example. The next example is a cantilever beam having a point load in the middle. So for this one also, if you draw the free body diagram, you'll get like this. W, R, Y, R, X and M0. If you solve for the equilibrium equations, you will get like this. It is W, here it is Ry. R will come as W and again M0 will come as WL by 2. This will be acting at a distance of L by 2. Now in this one, we have to do the cutting of the beam before the point load and after the point load. Let's take the numbering as 1 and 2 respectively. Now, if you are interested in finding out the shear force or bending moment diagram for the range x is belonging to 0 to L by 2. So this is L by 2. This is L by 2. So x is from this fixed support here. Okay, so this is origin and this is the length L here. So if you want to from 0 to L by 2, you will take the left part of the first section, or the first cut. So if you take the left part of the first cut here, you'll get like this. So here you have W, and here you have WL by 2, and here you are having shear force V upward, and bending moment M anti-clockwise. So this distance is X here. So let's derive for shear force equation, bending moment equation. So V plus W is equal to 0, so V is equal to minus W. If you want to go the bending moment equation about this point, M anti-clockwise, W into X clockwise, W into L by 2 anti-clockwise. So you get M is equal to Wx minus WL by 2, or M is equal to W of x minus L by 2. Now if you want to have the shear force equation for the range x is belonging to L by 2 to L. So in this one L by 2 is not included, that's why I kept an open interval here. So here also in fact L is not included here. But anyhow you will be getting the same answer because at this point no point load is there. When there is a point load, the change will be occurring. So for that one, what you have to do is you have to take the left part of the second cut. Because anyways you write down the equilibrium equation, so you will take the left part of the second cut and get the answer. So if you take the left part here, it will come like this. So here you have W, anti-clockwise W into L by 2 here. And here you have V, upward, and anti-clockwise M. And again you have point load P, or W here. This distance is L by 2 and this whole distance is X. So X is starting from here. What's the meaning of this one here? So X is also starting from here. It's going towards this end. So if you write down the equations here, you'll get like this. Shear force equation. V minus W plus W is equal to 0. So this implies shear force is equal to 0. If you go with bending moment equation about this point, M anti-clockwise plus W into x minus L by 2, W into x minus L by 2, again plus WL by 2 will come. So other thing is W into x minus W into x is equal to 0. So you written moment about because of each and every force. So W into x minus L by 2 will be corresponding to the moment because of this force W. W into L by 2 this moment. W into x will be this moment. So if you sum up, you will get M is equal to 0. So these are the equations here. So you're going to plot them. V is equal to minus W, M is equal to W into x minus L by 2. So if you plot the bending moment diagram and shear force diagram, you're going to get like this. First one is shear force, V, and this is x. 0, L by 2 and L. So 0 to L by 2, where L by 2 is not included, this is the formula. V is equal to minus W. So you'll get like this. So minus W up to L by 2, where L by 2 is not included, that's why I'm putting an open interval here. It will be equal to minus W. But from x is equal to L by 2 to L, your answer is 0. So the graph will suddenly shift to L by 2 to L. This is how the shear force diagram is given. Now if you go with bending moment diagram, it will come like this. M, 0, L by 2 and L. So from x is equal to 0 to L by 2, we have to use this equation. When x is equal to 0, M is equal to minus WL by 2. So minus WL by 2 will come. But it's a linear equation. At x is equal to L by 2, it's equal to 0. So, but this equation is not including the range of the point of L by 2. Or this range is not including the point L by 2. So, open interval should be there here. So, just like this one here. It will come straight line like this. Now, from L by 2 to L, this is the equation bending moment is equal to 0. So, here both will be coinciding here. So, this function is not differentiable at this point here, but it is continuous. Because the left limit and right limit both are equal here. Understand? So this is how you're going to draw the bending moment diagram. Now let's go with the previous GATE question. It's from GATE 2015 paper. You can see the question from the slide here. A beam is loaded as shown in the figure. The bending moment in Newton meter at the point R is. So let me draw the whole beam diagram here. So the beam is in this way. So at the point P there is a hinge support. So we have P suffix Y, P suffix X. At point S, we have a roller support, so only vertical reaction, S suffix Y. So PQRS, 4 points are there. This is P, this is Q, this is R, and this point is S. Now, here, as the load is acting on that L-shaped bracket here, so that load will be transferred to the Q. kilonewton. So if you transfer the load from here to here, you will get the diagram like this. So here, this distance is 1 meter. So if you transfer the load from here to here, you will get a reaction force 10 kilonewton, and also a clockwise moment given by 10 kilonewton meter. So this point is P, this is Q, this is R, this is S. And at R we have a load of 6 kilonewton. And this is acting at an angle of 30 degrees. So we have the reaction forces like this, resolved forces. 6 cos 30, so 3 root 3 kilonewton, and in the vertical direction we have 3 kilonewton. So let's write down the equilibrium equations here. We'll get like this. If you take net force in x direction is equal to 0, this implies Px minus 3 root 3 is equal to 0. This implies Px is equal to 3 root 3 kilonewton. In the same way, if you write down the vertical force, sigma Fy is equal to 0. This implies you have to write down Py minus 10 minus 3 plus Sy is equal to 0. So Py plus Sy is equal to 13 kilonewton. Now let's take the moment about P. Net moment about z-axis is equal to 0. This implies moment about P, so 10 kilonewton clockwise. So minus 10 kilonewton meter, 10 into this distance. This distance is 2 meters. This is also 2 meters, this is also 2 meters. So 10 into 2 clockwise, so minus 20. So 3 into 2. So 3 into 4, 12. So we have minus 12. Afterwards Sy is there here. Sy into 2 plus 2 plus 2, 6. So plus 6 into Sy is equal to 0. So this gives you the answer as Sy into 30 plus 12, 42, 42 by 6. Sy is equal to 42 by 6. So this comes as 7 kilonewton. 7 6 are 42. So if you substitute in this equation, you'll get eventually Py is equal to 6 kilonewton. So you got the value of Sy, you got the value of Py. Now we need to get the value of bending moment magnitude at the point R. But at the point R there is a point load, so we have to take a cut before and afterwards. But here in this case, if you take the cut before the point R and you take this range here, that will not be including the point R. So we have to take the cut after the radius R, or the point R here. So what happens is basically, if you take the left part of this cut or right part of this cut here, that will be including this range, or that range will be including the point R. So let me draw that thing here. So either you can go by the left part, which is like this. So here you have Py. So Py is coming as 6 kilonewton. So here you have 10 and a moment given by 10 kilonewton meter. And here you have a point load 3 kilonewton. And you have anti-clockwise moment because it's a positive plane. M is here. So this total distance is x, and this distance is 2. This is again 2. That's it. So if you take the right part, you'll be having like this. So here we have Sy. Sy we got it as 7 kilonewton. So no other forces are there. So if you go with the bending moment, so here it should be taken as clockwise M. So if this is taken as x, so this distance will be coming as 6 minus x. We can go by this left part by taking the moment about this point to get the value of M, or I can go by this part also. But anyhow, we go with this one to make it easy to get the answer here. So M clockwise, so negative M. If you go with this one, so plus 7 into 6 minus x is equal to 0. So you get M is equal to 7 of 6 minus x. 7 of 6 minus x. But here they are expecting us to get the value of the bending moment at the point R where x is equal to 4. So M at x is equal to 4 will come as 7 of 6 minus 4. This come as 14 kilonewton meter. But they are expecting us to enter the answer in terms of Newton meter. So bending moment M will come as 14,000 Newton meter. You will get the same answer if you go with taking the moment about this point also on this section here. Okay, thank you so much. So this part actually has covered only the drawing of shear force diagram, bending moment diagram. So if you are taking admission and coming for the class of shear force diagram, bending moment diagram, you'll be having the lecture of the whole thing. Thank you so much. All the best.